Welcome to Calculus. Today we will investigate solving related rates problems. We'll look at two different examples, one involving a triangular prism, the other involving an obtuse triangle. Our first example is about a public swimming pool that is 30 meters long and 5 meters wide. Its depth is 3 meters at the deep end, 1 meter at the shallow end. If water's pumped into the pool at the rate of 15 cubic meters per minute, we want to know how fast is the water level rising when it's 1 meter deep at the deep end. So let's draw a diagram so we can keep in view what type of geometric solid we're looking at. So it's a rectangular pool with two different heights. So at the shallow end, that height is 1 meter. And then at the deep end, it's substantially more deep. That's why they call it the deep end. It's 3 meters at that end. Now, water is being pumped into this pool. And so, as you can imagine, most of the water is going to collect down here at the deep end. In fact, it will all be there up until the water reaches the very foot of that wall that's a meter high at the shallow end. So we've got this view of it. If we were to turn it on its side and look at the pool from a side view, we would see that it's really kind of a quadrilateral type shape there, like a trapezoid. But because we're filling it up with water, really what we're seeing is, in fact, a series of successive right triangles. And that's going to persist until this pool fills up to the moment to where that water is from the deep end wall all the way to the foot of the shallow end wall. Now, we need to put some of these variables that we're seeing here in the pool in a list. That's our first go-to step when we're dealing with the related rates question. So my variables here definitely would involve this height of the pool, because that's what we're measuring as the water's filling up. So I'm going to put H, we'll represent that as height. And then again, we're filling the pool with water, so we're interested also in the volume. One other item is changing that we'll have to account for, and that's this, we'll call it B. It's the surface length, or the length of the water surface. Let's put it that way. We'll call it B, and that's the length of the water surface. And again, we're really only considering up till the moment where it's no longer a right triangle. So there are our three variables, and then we need to consider what sort of rates we're looking at in the question. So definitely we know something about the volume of water being pumped into the pool. It's 15 cubic meters per minute. So that's the change in volume at a certain time would equal 15 cubic meters per minute. That's constant. We also know that we're looking for the rate at which the water level is rising. So that's going to be represented as the change in height over time, and that's our question mark. We're looking for that. Now, the last thing I'm going to put here in terms of organizing the information is the detail measurement here. We're interested in this change when the height is 1 meter at the deep end. So at that point, we need to bring our information together in an equation that could relate these items. So I got to think about how I would calculate the volume of water that's filling up this pool. Again, I got to go to geometry and think about how I would calculate the volume of a triangular prism. So that type of equation would be volume equals the area of the triangular base. So that's half times the base, and again, that's the length of the water surface, times the height, which is the height of the water on the deep end wall times the height of the prism, which we'll call L, the length here. And we hadn't labeled that yet. We'll go ahead and label it now. That's a constant of 5 meters. So it's 5 meters across that pool the whole way. And in fact, what we can do here, before I differentiate, I need to kind of survey my equation to think about what variables I can deal with and which ones I want to modify. So volume definitely is good, height's good. Length, I know I'm going to fill in with 5 meters since that's constant, it's not changing. But I need to deal with this variable B, the length of the water's surface. I don't want 3 variables in my equation because I don't have information for all of them, and I don't want to deal with the change of that length over time as a rate. So what I can do is think back to how the legs of a right triangle relate in terms of proportionality. So I'm looking here at my side view of the pool. Each of these different right triangles based on the height of the water is proportional in length to all of the others, up to this one in green where it's all filling the pool from side to side, but not started climbing up the shallow end yet. So if I were to put measurements, that's 30 meters at the maximum there. Since the shallow end's 1 meter and the full deep end is 3 meters, that means that this height, when we're still dealing with a triangle and not a trapezoid, is going to be the difference. So that's 2 meters. And since all those triangles are proportional lower than that, what I can see is that the base is 15 times the height. That base is 30 meters long at that point when the height over on the deep end wall is 2 meters. I can see that relationship, B equals 15 times H. Now that simple relationship allows me to call the B variable in my equation 15H. I'm going to make a substitution there. So if I'm going to bring all the other pieces down, I'll bring the half, the volume, and the H, and we can further simplify this equation. Volume equals 15 times 5, that's 75 meters over 2. In fact, that's going to be meters squared because the 15H is a meters value, times H squared. Actually, I believe that I need to take that square off. In fact, that's perfect. And that completes my volume equation. So what's good to notice there is it's really in 2 different variables only. And at this point, it's ready to differentiate. So I'm going to do that now. I'm going to apply ddt to both sides. So we'll differentiate with respect to time. So on the left there's just v, so it's going to go down to 1. And what it's going to leave is dv dt. On the right side, the 75 over 2 is a constant, so it's just going to be like a coefficient. And then I'll take derivative of h squared, that's going to be 2h dh dt. And at that point, I want to then simplify this if I can. I see I can divide my 2's out. And I need to solve for the variable I'm looking for. So I'm looking back up here, I'm looking for dh dt. So I want to solve for that. So really all that's going to be divided is 75 times h. And I'll divide the left side by 75h. And this is what we've got as our current equation. Then we've got dh dt equals dv dt over 75h. So I'm going to fill in with those values. I'm going to substitute in. So dv dt has the value of 15 meters cubed per minute. And I'm going to divide that by 75, I'm sorry, times the height that we're interested in, which is 1 meter. And again, this 75 itself is a meter measurement. So what we're looking at when we simplify that is really 15 over 75, which again would reduce down to 1 over 5. And if I cancel my units correctly, that should be meters per minute. And that is our solution. So the water rate of the height changing rate at when the water is 1 meter on the deep end is 1/5 of a meter per minute. So that's an example that involves volume of a triangular prism. Let's investigate a situation that involves an obtuse triangle. So this is a scenario where a peregrine falcon flies up from its trainer at an angle of 60 degrees until it has flown 200 feet. It then levels off and continues to fly away. If the constant speed of the bird is 88 feet per second, we want to know how fast is the falcon moving away from the falconer after it is 6 seconds in flight. So if I just draw a diagram to visualize this situation, I've got the falconer there on the ground, and initially that bird is going to fly at an angle of 60 degrees from the ground into the air, and it's going to fly for a distance of 200 feet. That's just told to us in the paragraph. At that moment, when it's flown 200 feet, it will level off. So it's going to fly parallel to the ground until it's flown for a total of 6 seconds. Now, if I complete the sides of this triangle, I really am interested in what this angle that the bird is making as it flies over. So I can see that by creating another right triangle here on the ground first. So if that's a 90 and that's a 60, this angle must be 30. And since this upper side's parallel to the ground, that's going to be 90. So that angle has got to be 120 degrees. So we'll mark it as such. And really, that's the angle we're going to deal with here in this situation, 120 degrees. And then the bird itself, after 6 seconds, is out there at the far reaches. So what we're interested in is how fast is this distance from the falconer directly to the falcon changing after it's 6 seconds into its flight. So let's label these sides. I'm going to call these vertices A, B, and C. And so in terms of labeling the sides, the opposite side from A will be A, opposite side from B will be B, and opposite side from C will be C. So we're really interested in how the rate of C is changing over time. So at that point, we probably should label some of our variables. I'm really having two variables here. It's that distance A, so the length of the level flight there. So we'll call that the length of level flight. And I'm also interested in side C, which is the length from falconer to falcon. And it's not a right triangle, but it is akin to the hypotenuse of this triangle. It's the longest side, length from falconer to falcon. So calling it C is appropriate for where it is in the triangle. Now, that brings me to our rates that we're interested in. So definitely I'm interested in dA dt, and that's going to be dependent on the speed of the bird. Well, we're told that that is 88 feet per second constantly. We're also interested in dC dt, and as we saw in the question already, that's what we're trying to find. What's the rate of change of the distance from the falconer to the falcon at specifically 6 seconds? So we do have a time that's given at 6 seconds. Now, we're not really dealing in time in terms of our relationship. So what I want to kind of convert that to is, do I know some specific A value which I could use to come up with a specific C value in this triangle? So let's deal with finding the A value first. So I know that the bird is flying at a constant speed of 88 feet per second. And if we're catching this bird in its flight after 6 seconds have passed, we could calculate its entire length of its flight, both legs AC and CB, if we multiplied the, well, we'd be using this equation, distance equals rate times time. So the whole distance of the bird's flight would be the 88 feet per second times 6 seconds. So if we calculate that out, 88 times 6 is going to multiply to 528. My seconds will cancel and we're left with just feet. Now I can find the length of A if I just subtract from it the length of B, which is fixed at 200 feet. So that 528 is the length of the whole travel of the bird after 6 seconds. And I'm subtracting this constant value of 200 from it so that I can find this distance CB, which I'm representing as A. So that's going to be 328 feet. So I'm going to go ahead and label that here on the diagram, and I'll put it here that my A is 328 feet. Now, I should also come up with a value for C. So if this were a right triangle, we could use Pythagorean theorem. It's not a right triangle, it's an obtuse triangle. That angle's 120 degrees. So I can't use the Pythagorean theorem, but I can use the law of cosines, which is really a version of the Pythagorean theorem. So it really starts off the same, a squared plus b squared. But then to account for the non-90 degree angle, we would subtract the product 2ab times the cosine, which gives it the name law of cosines, cosine of c, and that would equal c squared. So it does have quite a bit in common with Pythagorean theorem. So I want to come up with the value for c at this instant at 6 seconds. So I'm going to plug in here what I know for A and B and the angle C. So that's going to be substituting in A, which we just calculated is 328 feet squared, plus side B, which is constantly 200 feet squared, minus 2 times A, which is again 328 feet, times B, 200 feet, times cosine of C, which I know to be constantly 120 degrees, and that equals C squared. Now I want to find C, so to do that, I'm going to take the square root of both sides, and what that gives me is this approximation. C is about equal to, well, let's put the exact version and then we'll put the approximation. So it equals the square root of 213,184, and that's not a perfect square, so it approximately has the value of 461.719 feet. So we'll put the exact version here with our data. So we did have to do a little geometric calculation to find really C. We just use distance equals right times time to find A. Now, we've done all that, and as we look for some kind of equation to relate my variables, A, C, and so forth, I don't have to look any farther than the law of cosines. That's actually what I want to use to approach taking the derivative and solving for dc dt. So what I'll do is I'm going to take that formula, which is again a squared plus b squared minus 2ab cosine of angle C equals c squared. Now there's some values here that I can substitute in directly because they're constant values. So I see that b is always going to be 200 feet. So we'll substitute in 200 feet for b, and that's going to be squared. A squared I'm going to leave as is because it's changing, and that's one of the rates we're interested in. So I'll leave 2a, but again, I'll substitute in b as 200 feet. And I can also put in cosine of specifically 120 degrees. And that all will equal c squared. So by making those substitutions for the b value and also the angle C, I've now reduced that equation down to just two variables, a and c. So let's simplify it so we can see what we're looking at. It's, a squared plus 40000, so 40,000 square feet, minus, so cosine 120 is going to be negative half. And if I multiply that times negative 2, that's going to make this positive 1 times 200a, and that equals c squared. So now that's a simplified version that now I can take the derivative of. So let's apply the derivative here. So dt will take the derivative with respect to time of both sides. So there on the left side, what we'll see is we've got 2a dA dt plus 0. The derivative of 40,000 is 0, plus 200. A becomes 1, but I multiply times dA dt as well. And that equals 2c dc dt. So now I've got that differentiated. I want to then solve for the rate that I am looking for. So I'm looking for dc dt. I'm going to circle that. So on the left side, if I simplify this down, it's going to be 2a plus 200. If I factor out that they both have that dA dt, then I'm going to divide that by 2c, and that will equal dc dt. So at that point, I've got the derivative, and all I need to do is plug in my values for a and c and dA dt, and I should be able to calculate this rate. So it's going to be, and in fact, what I can do here, I see I can divide out a 2 here in all terms and change that to 100. So even that will simplify more. So now I'm going to plug in my a value, which we found to be 328 feet. plus 100 all over C, which we calculated to be the square root of 213,184 feet. And then I shouldn't forget dA dt. That's going to be 88 feet per second. And that is going to be equal to dc dt. Again, that's what I'm trying to find. And again, that expression on the left is exact. If I run it through a calculator, I'll get the approximate rate of change of 81.574 feet per second. It's a fast bird. Well, thank you for joining this investigation of 2 related rates questions. I'll let you solve your own related rates questions. Thanks for joining. See you soon.